lesson, section 7.4, exponential growth and decay. And to start this, what we're going to look at is the method that is used to derive the formula for continuous compounding, the formula for radioactive decay and half-life, the formula for Newton's law of cooling. And we have already talked about this in the previous section because I warned you it was coming. So a separable differential equation is a differential equation of the form dy dx equals f of y times g of x, and that is called separable. The way we separate the variables, just as we did earlier, is y with dy, x is with dx. Things to remember when you are separating variables: we never want a dy or a dx in the denominator. We always want to have multiplying by dy or dx. So that helps you in deciding how to move things. Okay, just background, nothing really important to write down in the notes for that one. We have actually already been doing these, and we're going to start with our first example of solving a separable differential equation. So, here, can you see that in the back? Yeah. Try to make it a little bit bigger. We're going to solve for y if dy dx equals quantity xy squared and y equals 1 when x equals 1. What does it mean to solve a differential equation? What are we looking for? The original function. We're looking for y. So if the directions only say solve dy dx equals xy quantity squared, you know you're looking for y. Okay? So what would we do here? Let me rewrite. Dy dx equals quantity xy squared. What would you like to do first? Multiply, sorry? Sure, we can do that. We can get dy equals xy quantity squared dx. Then what? Yes. Not yet. No, we need to solve it first. Solve that differential equation for y first. So that would mean we would have no dy and dx's left. Well, can we differentiate x and y together? We should put x squared y squared. We should put x squared y squared, yes. So we can move things. We want dy equals x squared y squared dx. Remember, our goal is to get y's with dy's and x's with dx. So what shall I move now? Y squared, yes. Divide by y squared. So now I have, and I'm just going to rewrite it in a way a little easier to see, 1 over y squared dy equals x squared dx. Okay, now what? Integrate. Integrate, yes. Integrate both sides, yes. So we're going to put in our integral here, and our integral here. And on the left, what will we get? Well, let me write it. I saw this error a few times on the quizzes. How do we integrate 1 over y squared? What do we do? Bring it to the top and write it as y to the what? Negative 2. Okay, and then to integrate it, what do I do? Y to the negative 1 over, good. Which equals negative 1 over y, correct? Coming up here. So I have negative 1 over y. And I'm going to go ahead and show you what I told you about before. And I'm going to add my constants on both sides, just so you can see why it is I keep saying we'll only manage them on the right. Okay? So I'm going to put a plus b1 right there. equals, how about on the right side, what do we have there? 1/3 x cubed, or x cubed over 3, plus, we'll call it C2. Okay, when you're solving a separable differential equation, you want to get y by itself, if possible. So what would you like to do? You're combining two steps, I can see it already. We will be multiplying that y over. But first, what shall we move? The C1, let's move that C1, minus C1. So I have negative 1 over y equals x cubed over 3 plus C2 minus C1. Okay, that much. By negative 1 we can divide, actually, right, because it's on top here. Divide by negative 1, so we get 1 over y equals negative x cubed over 3 minus C2 plus C1. Okay? Now what?
Since it's negative, why is it still plus? Oh, never mind.
I switched them. Yep.
Do you multiply by y?
We're going to multiply by y and then divide by everything else. But right here, I'm going to rename my variable, not my variable, my constant. I'm going to say let's let C equal negative C2 plus C1. So now what I have is 1 over y equals negative x cubed over 3 plus C. That way I don't have to keep pulling two constants with me everywhere I'm going. Okay? I'm just naming some other constants be the sum of these two constants. A constant is a constant, has the same effect here. So, you said multiply by y and divide the negative x cubed over 3 plus c to the other side. So I see 1 over negative x cubed over 3 plus c equal to y. Yes? Now what? Plug in. What do we do now? I multiplied by y and I divided this side over to a y. So I combined two steps.
There's no y in that. Did you multiply negative x cubed over 3 by y? You know.
I'm going to keep a parenthesis. So it would be like this. Okay? And then I would just divide that negative x cubed over 3 plus c and solve for y. Other questions?
What read of your negative x would go on top?
Not yet. Not unless you combine the fractions on the bottom, right? If it were multiplication on the bottom, you could, so don't make that mistake. If you want to combine these two on the bottom and write it as one fraction, then you can flip the denominator up. All right, so we're going to plug in x equals 1 and y equals 1. That's the 1. And we are going to get, so I can go down here, we are going to get 1 over negative 1 over 3 plus c equals to 1, yes? Thank you. Don't let me forget my cube. And it is negative outside and the 1 is cubed. So we will end up with a negative 1/3. All right, now what? Solve for c. What do we do? Multiply by the negative 1/3 plus c. On both sides. And on the left, I have 1, and on the right, I have negative 1/3 plus c. Finally, solve for c. Add 1/3. So I have 4/3 So my final solution, my particular solution, is going to be 1 over negative x cubed over 3 plus what? Plus 4 thirds. And that is it, equals y. So now, James, they both have the same denominator. Now we can put that together, yeah? Okay. So that is our solution. Write yourself a couple of notes. You want to get y by itself. It doesn't have to be y to the first necessarily. You want to get y alone. And then secondly, your solution should always be a function. That's very important. Your solution should be a function. So write that in. And for example, let's say I had my solution came out to be y equals plus or minus the square root of 2x squared plus 7x plus 5. Is that a function? Why? You're right. It does not pass the vertical line test. So you would then have to figure out where is this going through. Will I want the top half of this sideways parabola or the bottom half? Okay? Yes, Dan?
The T2 and T1 doesn't matter.
No, because we renamed them to be just T. So all we need to find is just T. Just a constant, not variable, so we can just rename it and say we're just finding 1 instead of 2. Start here, reminder. Okay, any questions on number 1? Separating the variables and solving the differential equation. All right, so this is just reading. This is not something you have to write everything down for. Let's just find out where this is coming from. So the law of exponential change. Let's just read through it so we know what we're looking at. You've probably solved enough exponential growth problems by now to recognize that they involve growth in which the rate of change is proportional to the amount present. All right, so underlining that, rate of change is proportional. Okay, yeah, it feels like I'm drawing a straight line. Okay. So rate of change, what's another name for that in calculus? Acceleration is an example of one. Derivative. Rate of change is derivative. And remember back in pre-calc in ELF 2 when you did direct variation? Something is directly proportional to something else, so you would write the equation y equals kx. Remember? So they're saying the rate of change, dy dt in this case, is proportional to, so that means it falls into that direct variation format. So we can write the equation, dy dt equals k times the amount present would be y. Okay? This differential equation is the basis for continuous compounding, radioactive decay, Newton's law of cooling. All of those models come from this differential equation. Okay? All right. The more bacteria in a dish, the faster they'll multiply. The more radioactive material present, the faster it decays. The more money in your bank, the more money you grow. Okay? Exponential growth and decay. The differential equation that describes this is right here as we discussed, where K can be positive for growth and negative for decay. All right? So let's see where this comes from. Let's see if I have this. We're going to do it right here. All right. So what I want to do is solve this differential equation the same way we just solved our first example. So what do I do to solve this guy?
For DP.
Multiply by dp, okay. So I will have dy equals ky dt. And what? What do we do? Divide by y. Just so you know, anytime I have a constant, I don't move it. I don't bring it with the y, I don't bring it with the function. A constant means multiplied, I just leave it where it is. So now I have 1 over y dy equals k dt. What's next? We've separated our variables. Integrate both sides. All right, what do we get on the left? Natural log of the absolute value of y. Equals, and on the right, the integral k dt. K is a constant, kp. And let me be, so in this problem, we are just going to manage our constants on the right. Because we showed what we would just do, we would end up managing on, putting them together and managing them on the right anyway. Okay. All right. I want to get y by itself. Help me. How do I get rid of that natural log? E to the power of both sides. So e here and e here. And on the left, the e and the natural log undo each other. And we are left with the absolute value of y equals e to the kc plus e. All right, a couple of things that we will do every time is on the right, when I have an exponential with addition in the exponent, I can rewrite that as e to the kc, and then what? Times e to the c, very nice. We still have absolute value of y on the left. All right, so once again, you'll get used to defining your constant. Well, e to the c is just a constant, right? E is a constant raised to a constant. So here, we are going to say let, and I'm going to call it y sub 0, and I'll show you why in a second, equals plus or minus e to the c. All right. See if you can help me. Why would I call it y sub 0 for the constant that I get in front there? What does sub 0 usually mean with the original, right? The initial condition. Well, if I put 0 in for t, wouldn't I just be left with a constant here? I'll show you that in a second. Why would I put plus or minus on my e to the c? What's that going to help me get rid of? The absolute value. Yeah. Instead of, by saying my constant can be a positive or negative e to the c, that accounts for what will happen over here. And now we can just write y equals y sub 0 e to the kc. So what I was saying before is if I put 0 in for my t, this e to the kc becomes 1, doesn't it? And my y value would equal my initial y value. So that's why we go ahead and put in y sub 0. Okay? All right. So think about, does anybody remember continuous compounding model? When we were at a bank, and we're continuously compounding. What's the equation we use? Yeah, what is it? Hurt. It's the Hurt equation, yeah. Which is P times e to the RT. Right? Where R is constant for the equation we're looking at. So the continuous compounding equation comes from the differential equation we just solved. All right, and we'll see that also radioactivity and Newton's law of cooling come from that. But this is the important basic equation that we get when we solve dy dt equals ky. All right, let's see what else we have. So this is exactly what we just derived. The law of exponential change says if y changes at a rate proportional to the amount present, and if y equals y sub 0 and p equals 0, then we get y equals y sub 0 e to the kp. K is called the growth constant if k is greater than 0, the decay constant if k is less. All right, so this one is derived the same way. We've seen this year after year, correct? This is continuous, this is compounding when we are not doing continuous compounding, maybe monthly or yearly or biannually. So I just want you to see that you will have to be working with this equation as well as A equals P times e to the R. And this is the one that we use for continuous compounding. And up here we are compounding K times. So these are just reminders of equations you've dealt with in the past that could pop up in your homework. So we would use this one if the problem said we're compounding twice a year, and or if they said, every month. We would use this one. We would use this one if they use the word continuous compounding. That means it's compounding at all times. And you could think about this, you end up getting this one as like an infinite sum. They're compounding an infinite number of times, which brings us into calculus. All right. So, radioactive decay. You don't need to read through all of this. We've dealt with radioactive decay problems before. It falls under the same type of problem. dy dt equals negative k y. It's negative because we are decaying. And when we solve that differential equation, again, we get this y equals y sub 0 e to the negative kt. Let me see if I can do something like this. Okay. All right. Let's move on. Modeling with the same basis. You'll run into, possibly running into that. I don't see that very often. We're not going to go through that example. We will go through this Newton's law of cooling. So, Newton's law of cooling deals with a situation where if you take something at a certain temperature, an object at a certain temperature, and let's say it's at 100 degrees Celsius, and we bring it into this room, what will happen to the temperature of that object? Sam? It's going to cool down to what temperature? To the room temperature, to the temperature of the surrounding. Okay? That is the idea behind Newton's law of cooling. Okay? And we can again model this using a differential equation. So this observation that I just described is called Newton's law of cooling, and it applies to Harmony as well. Let's see, T. So here's where we need to identify what we're talking about. So when solving this differential equation, we end up with T minus T sub s equals, the quantity T sub 0 minus T sub s times e to the negative kp. Well, we need to know what all those T's are. Unfortunately, there's a lot of T's. So capital T is the temperature at any time. T sub s is the surrounding temperature. So here it would have been room temperature in the example I gave. Surrounding temperature. T sub O, initial step. K is our growth constant. Or decay constant. Oh, yes. If it's all right. And little c is time. There tends to be just a lot of information given in problems to deal with this model. So just keep track of your variables. Yes. Yes, thank you. T sub O. There's no there. Thank you. So we have T, capital T sub S, capital T sub O, and K. And then small, lowercase t is time. All right, so we have two examples. Oh, I think it's three examples. Two of them come directly off your homework. Okay, so Newton's law of cooling. A hard-boiled egg at 98 degrees Celsius is put in a pan under running 18 degrees Celsius water to cool. Okay, so what have they given me so far? Initial, T sub O is 98 degrees. And what else did they give me? Surrounding, T sub S. 18 degrees. Okay. After 5 minutes, what's that? Time, our lowercase t, is 5 minutes. The egg temperature is found to be 38 degrees Celsius. What is that? That's just, okay. How much longer will it take for the egg to reach 20 degrees Celsius? So that is a second T, correct? That they've given us? Second capital T. All right, so let's write down. We have T minus T sub S equals, what is it, T minus T sub O? Or T sub O minus T sub S? Which one is it, T sub O? Yeah, T sub O minus T sub S. Times e to the negative k little t. All right, in these cooling problems, the first thing you want to try and do is solve for k. Well, I have T sub O, I have T sub S, I have time, and I have my current temperature. Do I have enough to solve for k right now? I do. Let's plug in. So we have 38 minus 18 equals 98 minus 18 times e to the negative k times what? 5. we get 20 equals 80 e to the negative 5k. Is that answer? E to the negative 5k. Now what? What do I do next? Divide by 80, and we end up with, we get 1/4 equals e to the negative 5k. Continue. Natural log equals negative 5k. And finally, divide by the negative 5. And so we get k equals negative 1/5, the natural log of 1/5. In your book, they tend to switch their logs of fractions to be negative logs of the whole number. I don't care about that. I don't care if you switch it to be that way or not. This is the constant, and I'm fine with that form. All right. So then, what we really want to know is how much longer it's going to take for the temperature to reach, what? 20? 20. All right, so tell me, where am I plugging in now? So, do I have my P? That's 20, right? So 20 minus, what? 18 equals, my initial is still 98, minus 18, e to the, can somebody give me a decimal for that, please? For my k? Negative 1/5, natural log of 1/4. Point. 4277. Does that sound familiar? Does that sound right? Did anyone else check it? Stan? Same thing? Okay. All right. Times P. All right. Take a minute and solve for our little P. Our K came out to be positive, 0.277?
Yep.
Yep. So that should be negative, thank you. We should have calculators out, folks. Don't just let other people do it. Finish it up for me. In minutes. Yeah. Survey, do you have it? No. 13.3 minutes. There we are. Do we agree? Yeah? Good. All right, good. So there's your cooling problem. Little practice there. Let's take a look at 21. We'll look at 21 from your homework and 31. And work through these together. So, 21, the radioactive decay of SN151, an isotope of samarium, can be modeled by the differential equation dy dt equals negative 0.0077y. So let's start with that. dy dt equals negative 0.0077y. Where t is measured in years, find the half-life. All right, so they started us with our differential equation. We should be able to tell what the form of our solution would be because we've done it already, but I want you to go ahead and separate these variables and come up with our y equals equation. Do that now, please. I'll be doing it up here at the same time. And then we'll double check. You should be working this on your paper. That's what mine is. Again, we come up with that constant times e to the kt. Okay? Yes, go on. What negative? Oh, it should still be there. Should not disappear. Having issues with my negatives today. Thank you. All right. So then it says find a half-life. Well, if y sub 0 is our initial amount and y is our current amount, the first thing I would do is divide that over, and what would I have? If I'm talking about a half-life. Not 2, but a half. Yes, we'll have half of what we started with. So to solve for half-life, we can always just set our y over y sub 0 equals to 1/2. Equals e to the negative 0.0077c. Solve that, please, on your paper.
What does it say? Y sub 0 is equal to plus or minus
C. See if I can write that a little clearer. Plus or minus all right, solve please, and tell me what we get for our half-life. How much? 19 point. Give me 3. 0.19. Years. Sorry, 19. Oh, 90. 90.019? Got it. So we would take the log of each side. And divide by negative 0.0077. To get our, okay? All right, final example, and again, off your homework, should I say their product?
I was wondering, when starting the 1/2 of the y, that's the half-life, right?
They asked for a half-life,
yeah.
yes.
Where's the y sub 0 and the 1/2?
Actually, if you look right here, what I did is y over y sub 0 is equal to 1/2. Because whatever you started with, you end up with half of that at the half-life. Okay. All right. And let's move forward. All right. So another cooling one. We have the cooling soup. Suppose that a cup of soup cools from 90 degrees Celsius to 60 degrees Celsius in 10 minutes. So 90 degrees Celsius is what? T sub 0. And our T, capital T, will be 60 degrees Celsius. And our time, little lowercase t, is 10 minutes. And in a room whose temperature is 20 degrees Celsius. So what's that? T to the. Okay. Use Newton's law of cooling to answer the following question. How much longer would it take the soup to cool to 35 degrees Celsius? So here we go again. There's our Newton's law of cooling formula. So the first thing we're going to do is solve for K. Do this at your desk. I'll do it up here. Asking for 35 degrees, to cool to 35 degrees. I get a K equal to 0.056. Do you agree? Okay. Now, we need to read the question carefully. I believe it said, how much longer will it take? So be careful when you give your answer. I'm getting T equal to the natural log of 15/70 over negative 0.056. Which gives me, does anyone have it? 27.5 minutes. All right, but they asked how much longer, so how much longer is that? 17.5 minutes longer. Okay, so there's our solution, 17.5 minutes longer to cool to 35 degrees. All right, let's take a quick look. Instead of being left to stand in the room, the cup of 90-degree soup is put into a freezer. The temperature is negative 15 degrees. How long will it take for the soup to cool from 90 to 35 there? So what's going to stay constant this time? I mean, what's going to be the same? The K. Yep. All right, we've already solved for K. So we can use that to help us in the next part. So go ahead and do part B. Our constant is already solved for. And we have negative 15. Solving for time, the time it takes to get to that negative 15. So I plugged in my numbers. I'm skipping a couple steps as I go through. There is my T calculation. Solution, what's T? 13.25 what? 250 minutes? Okay. do it. And there is your solution. All right, so the last two examples came from your homework, and your homework for the long weekend is in section 7.4, 1 through 33 odd, and 47 through 52 on page 361. It will be checked on Tuesday. Notice that Tuesday is our last section for this chapter. Your test starts next Friday. There'll be a no calculator and a calculator for the next Friday, Monday. Okay, keep that in mind. All right. You can get a few more done.
Did you collect those 20,000 that were due?